Okay, so let's start with question 1. And that one talks about a little boy in an RV. And so when he is sitting in the RV, he's basically at rest with respect to the RV, because he's moving with the RV. So it doesn't matter whether he shoots it to the front or to the back, he's going to have the same range. Now, part B says, what if you're an observer outside of the RV? So if you're an observer, RV's going that way, he shoots it that way, as opposed to RV going this way and he shoots it that way. These are in the same direction, so you're going to see it have a greater range here. Than in this situation, because these two are in opposite directions, so the actual velocity that you see is going to be this value minus that value. So it's going to have a smaller range because of your perspective of where you're seeing it. You're standing outside. Okay, number 2 says you shoot a projectile at some angle theta, and you call that velocity A, and it just so happens that your velocity A is 2 times what you shot it with during time B or situation B. And it wants to know, how does the height compare in those two situations? So I'm going to call it a height comparison. And then we want to do a range comparison. Now, if I shoot it twice as, if VA is 2 times VB, then it's going to take, in situation A, the time of flight is going to be 2t. And in situation B, because it's slower, the time of flight is just going to be b. It's just going to be t. So if I look at the height comparison, I'm going to say that d is equal to byf squared minus byi squared over 2g. Well, this is the same regardless of whether I'm A or B. This is going to be 0, so regardless of whether I'm A or B, it'll be the same. So the distance for A is going to be 2, and we can ignore the negative sign because that's a negative g. So it's going to be 2 times the cosine of, well, hang on. I don't want cosine because I'm talking about y-axis, so I should have said 2 sine theta VA, and VA is 2VB, so I'm going to put that in there. So when I do that, don't forget you got to square it. So dA is going to be 4 sine squared theta VB squared, and dB is going to be the exact same thing. It'll be dyi, which is the sine of theta VB. And I'm going to square that. So when I compare them, this one is 4 times. Now when let's go ahead and square that out. So that's sine squared theta VB squared. So this one has 4 times as much value as that one. So the height comparison, height of A compared to height of B, is going to be 4 times to 1. Okay, now range dx equals dxt. So for A, dx is going to be 2 times the cosine of theta VB. And the time of flight is going to be twice as much. For B, it's going to be dx. It's just going to be cosine of theta VB. And it's going to be in flight for t time. So that's, if we can get rid of that. So that's 4 cosine theta VBT. And this one is just cosine theta VBT. So if I compare those, so if I compare dx for A to dx for B, that would be 4 cosine theta VB times t compared to cosine theta VB t. So again, ratio is 4 to 1. I'm going to go eat some supper and I'll come back and do some more. All right, so now I'm back, and let's look at number 3. So number 3 says that you have a glider. Is increasing, the altitude is increasing at 6.8 meters per second, so altitude would be vertical. And the shadow of the glider moves along the ground at a speed of 15.5 meters per second. So this looks like a vector problem to me. Find the magnitude of the glider's velocity. So Mr. Pythag is going to be my friend, so I'm going to say 6.8 squared plus 15.5 squared is equal to c squared. So when I did that, I believe that I got 16.9 meters per second. All right, that was number 3. Number 4. So when we look at number 4, it says something like, a dog walker meanders through the woods at Lick Creek Park, walking 5, blah, 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 blah. So we got to get all of that mess figured out. So I just made a little XY chart. X, Y. So it tells me that he went a half kilometer east, so that's 0.5. And 0.75 kilometers south. So that's going to be, and he had nothing there. And then negative 0.75 kilometers, and it's negative because he went to the south. And then it says that he went 2.15 kilometers in a direction 35 degrees north of west. So I'm going to draw that. Oh, north of west. I'm not going to draw it like that because that would be bad. So north of west. So he went here, 35 degrees. So there's his X and there's his Y. And his little distance was 2.15 kilometers. So I'm going to say X is cosine of 35 degrees times 2.15. And Y is sine of 35 degrees times 2.15. So when I did my X many moons ago, I got, let me make sure I'm telling you the truth here, 1.26 kilometers. And for my Y, I got 0.48, looks like to me. Okay, so my X is going to be a negative 1.26 kilometers. And my Y is going to be a positive 0.48 kilometers. And so if I did this correctly, let me pause and check something. Let's go. Yeah, I got some trouble. Let's see if we can fix it. I've already started recording 3 different times, and I just keep making stupid mistakes, so we're going to fix it. So this is the sum of them, so I kind of jumped ahead of myself there. Let's see if we can backtrack and get it together. All right, so if we backtrack and get it together, the X is 1.76, and the Y is 1.23. X is still negative 1.76. Y is positive 1.23. So now if I add those up, this is going to be negative 1.26. This is going to be positive 0.48. So now I should say 1.26, 0.48. I do my Pythagorean theorem. So C is going to be the square root of 1.26 squared plus 0.48 kilometers squared. So when I did that, and I did it correctly, I got 1.35 kilometers. And I need this theta. So tan theta, 0.48 over 1.26 And theta wound up being 20.9 degrees, it looks like. So I can say that that's 20.9 degrees north of west. I could also say that its pilot's bearing is 180 minus 20.9, which would be about a pilot's bearing of 160.1. Is that reasonable? Actually, 159.1 would be the pilot's bearing. So I could say it that way, the direction, and there's my magnitude. So there's number 4. Again, you can pause if you need to and check it all out. Let's change color, getting sick of green. 5. So 5 says an AMCHS, and actually I think here it says CSHS platform diver runs horizontally with a speed of 1.2 meters. It's coming out that way. Meters per second. And the platform is 10 meters above the water. So dy is equal to 10 meters. And they want to know what is his velocity just before splashing the water. So when he gets to where he's fixing to splash the water, here's the water, he has a VYF and a VX. His VX is still going to be 1.2. I need to find VYF. Well, it's going to be, I taught you VYF squared equals VYI squared plus 2G VY. When he runs off horizontally, this is 0 because gravity hasn't accelerated it in the vertical direction. So VYF is simply going to be the square root of 2 times 9.8 meters per second squared times the 10 meter height that he has to fall. So when I did that, I got VYF to be 14 meters per second. They want to know this right here and that right there. So this is 10. I'm sorry, how about 14? That's okay. So that's 14 meters per second. So I'll be there. Okay, so I'll do Pythagorean theorem to find B. Square root of 1.20 squared plus 14 meters per second squared. So B is going to be the square root of all that lovely stuff. And I got 16.8 meters per second. Now I need to angle with the ground. Well, that angle and that angle are identical because of alternate interior angles. So tan theta is 14 over 1.2. So theta is, according to Ms. Walker's calculation, 85.1 degrees with the water. Pretty steep, but that makes sense because it's quite a long way down. All right, then I think there's a part B. Let me see if I'm aligned here or not. Part B says, what was his distance from the bottom of the platform? So in other words, how far out this way did he travel? Well, we know that dx is equal to vxt, but I don't have a t. But I know that the dy, 1/2 gt squared, plus vyit. So that's 0. So if I want to rearrange this for t, t is going to be the square root of 2 dy over g. So it's the square root of 2 times 10, all over 9.8. So when I did that, I got time to be 1.43 seconds. So I know that dx is equal to dx, which is 1.2 times t. I only need that time because he's just falling down. He's not going up and then down. So he lands out from the base of the platform. Horizontally, he lands 1.72 meters away from the base of the platform. So there's number 5. I'm going to start a new one.